We had a look at a few examples yesterday, and we'll take a couple more examples today and start drawing some general conclusions. The approximation that we use for calculating instruction execution time on number 68000 is this. We assume that the only thing that takes time, the only things that take time are associated with bus transactions. So any internal operations inside the processor will take up no time. Getting information to or from anywhere in the processor, we assume takes no time. The operations themselves, we assume they take no time either. Okay, so it's pretty simple. So all we've got to do, when we want to find out how long an instruction takes to execute, is to count the number of bus transactions that it gives rise to. And they're of, well, 2 or 3 times, depending on how you look at it, possibly 4. But 2 general kinds. There's instruction fetching, and there's data operation. Okay, instruction fetching and data operation. Instruction fetching would be fetching the opword in any of the extension words. Operand fetching would be reading information from memory into the processor, and operand writing. So you could either read or write operands to or from memory. So they're the categories. Okay, instruction fetching and data fetching and putting away. Let's see if this thing has come back here. In half of a 4-letter word. No. So they haven't come back. So I'll just have to read out my notes. That's all. Pardon?
Should be able to force it to. It's probably just not output into the behavior.
Yeah. Okay. Right, so if we can count up the total number of bus transactions, we're in business. Now, we see there are a couple of little corrections we have to make to that assumption later, but it's actually a very good starting point. Now, a couple of things you have to bear in mind. You have to bear in mind what actually happens when an instruction executes. The instruction is fetched, data may be fetched from off processor, from memory, and data may be put back. You have to bear in mind it's a von Neumann machine. So when you see an instruction like this, move a word from, say, here, well, let's say from location, say 2000 to say 3000, you might think that what actually happens, just by looking at it, is a word is read from location 2000 and written to location 3000. That is not what happens. The von Neumann machine, nothing can happen in memory, and nothing can happen directly between memory locations. So what would actually happen in a situation like this is that the word of information would be read from location 2000 down to the processor. Okay, it has to be a participant down to the processor, and then it's written from the processor to location 3000. So you'd have a read operation of the data at location 200, and then a separate write operation at location 3000. Yes, sir.
Does the processor then have a spare an extra register to take data in?
Does the processor have a spare? It has quite a number of. Apparently, it has quite a number of what we might just call hidden registers. Yeah.
So
yeah.
It doesn't go into
It doesn't necessarily land in one of the registers we see. That's correct. Another example is one like this. Add.w, say, well, even let's try this. This be, say, D0 to, say, location 4000. Okay? What appears to be happening here, if you think about the meaning, the semantics of this instruction, is that the contents of D0 are added to the contents of location 4000 in memory. It seems like that. They're just sort of, it seems as if they're just shoved out and added into whatever is there. But that's not what happens. Okay? Nothing can happen in memory by itself. It only remembers things, you can store stuff out there and retrieve it. To give effect to this instruction, what happens is the contents of location in this example 4000 are actually read down into the processor, down to a hidden register, and the contents of D0, the word part of D0 is added to that, and then the result is written back out again. Okay? So the addition that happens, that's implied by this add instruction here, does not happen in memory. it happens in the processor. So you have to visualize that when you're trying to work out how long these instructions take. So that's quite an expensive instruction, even though it looks nice. There's a read from location 400, the add happens locally, and then a write back out again. Okay, if you were adding, say, long word D0 to be really quite expensive, but we go through the calculation of it. Okay, so then what I'm saying then is, in summary, to work out how long an instruction takes to execute, we calculate the number of bus transactions it gives rise to. We calculate that by looking at the instruction itself and its extension words. That's obviously part of the tariff, as it were. And then we have to watch what actually happens when the instruction is being performed itself. Okay, so not very satisfactory here. Okay, the extension words. Now, we've used the extension words. And the extension words, I'm just going to give you what extension words are used for. And I'm going to own up to using a new addressing mode that I used a couple of days ago and tell you about it. And there's one other and a final addressing mode I want to talk about as well. Okay, so in the context of extension words then, if we're talking about a quick, if we're talking about an immediate operand, okay, immediate operands, but not quick, okay? Then, okay, so we're going to make up a little table here. Okay. The next peculiarity that we have to look at is what we're talking about are transactions on the system bus, which we'll be talking about. For the moment, just bear in mind that the bus contains, or I should say, can carry one word. It's a 16-bit wide data bus. And so if we have a byte, an immediate byte, well, that's going to take, obviously it only really needs a byte of extension, okay? But in order to keep the instruction itself an even number of bytes long, that byte is fitted into a word, and the extra byte that's available is just not used. Okay? So an immediate operand of size byte takes one word, of size word obviously takes one word, and of size long takes two words. Okay? So if you were saying I want to move a long word whose value is 751, well, that 751 is going to occupy, that value is going to occupy two extension words in the instruction. Two extension words. So it's a pretty costly little thing. But there you go. That's the cost of doing business. Okay, so that's immediate operands. Now, quick immediate operands don't occupy any space in the extension words, as I said yesterday. The thing about quick immediate operands is they're made part of the operation word. So space is reserved within the operation word for quick immediate operands. Move quick, 8 bits of space. Add quick and subtract quick, 3 bits of space is reserved for them. If you think of the operation word as a resource for a moment, for naming different instructions that in principle the 68000 might be able to execute, the total number of possible distinct instructions is obviously 65,536. And a much smaller number than that is actually used. Nevertheless, when you take 8 bits off of, say, the space that's reserved for move instructions, you're taking quite a big lump out of the possible set of instructions that the machine might be able to recognize. So that would be a consideration. It's not much of a consideration when these are 16-bit operation words, but imagine you were talking about a machine that where you only were allowing 8 bits to specify an instruction. That could happen, 256 possible variations, so that could be an issue. Okay, immediate operands. Now, direct operands. Well, the only direct operands we need to worry about are absolute memory. Absolute memory operands. Okay, in other words, where you're actually specifying the address. We talked about this before. And we can have absolute memory short, okay, where we'll have one extension word. And we'll have absolute memory long, where we'll have two extension words. So this is the benefit, such as it might be, of absolute memory short and long. You remember that if you have a location that lies at the very top end of memory or at the very bottom end of memory, the bottom end of memory would be the first 32K locations, okay, from location 0 up to location 7FFF, okay, 0, 0, 0, 0, 0, 0, 0, 0, up to 7FFF. So if you've got a location in that range there, or if you've got a location at the very top of memory, from FFFF8000 up to FFFF, with the bottom 32K or the top 32K, then you will be able to reference it, if you want to reference it using an absolute addressing mode, you can use absolute memory short. You can represent the location using one word, and that word is sign extended out to a full 32-bit address. Okay? It makes the instruction itself shorter, okay, because you only need one extension word, and it's a little bit faster, therefore, to fetch. Okay? So it's a little increment. In general, however, you're going to need two extension words to represent a full address anywhere in the 32-bit address space. Okay, so those are familiar enough. Now, two new addressing modes. Okay, two new addressing modes, and so these are indirect. I should actually rename this direct operands, should be direct modes. Okay, indirect modes here. Okay, now if we go through the indirect modes that you know, address register indirect, okay, where the memory location is actually in an address register. Well, it's in an address register, it's on the processor, doesn't need any extension words and so on. The only indirect modes that we need to worry about are two new ones, and one is called address register indirect with offset. Okay, the offset is a 16-bit signed offset. And it's fixed when you write the instruction. So you might say, the way you might say it and the way you might write it, you might say, I want to say move a byte from 4 past A0. Okay, so there's the syntax of it there. The brackets indicating address register indirect, and preceding it a fixed offset, which in this example here is a number, and it's signed, so it can be from 4 past A0, or you could have, say, for example, -4. I mean, I would say this as -4 past A0 rather than 4 before A0, but it's up to yourself. Okay, so you can have a fixed 16-bit signed offset. Okay, a fixed 16-bit signed offset. Okay, so coming back to the way the instruction is encoded, the 16-bit offset that's part of this addressing mode will not be stored inside the operation word, it'll be stored as an extension word. Okay, so that's one extension word. And that's very useful. You might, for example, you might need an address register indirect with offset if you're with, say, walking through an array and you're getting the local average of, say, the local 3 items in the array. So you might be pointing at the central item. You might want to go back to the previous one, let's say, where your address register is pointing -2, if they're word-sized operands. And you might also want to reference the next one along at the address register location +2. So you might say something like this: move the word from -2 past A0, say to B0, add the word 0 past A0, or just brackets A0 on its own to B0, and you might say add the word from +2 past A0 into B0. So that would be a convenient, it would be convenient to do that using address register indirect with 16-bit offset. Okay? Yes? Yeah. Is it, well, if I could just change your question's phrasing slightly, does it change the value of the register? No, it does not. Okay, it does not say, in this example, subtract 4 from A0. It takes the current content of the register, adds this to it, and uses that as the effective address. And these A0 and 1. So you want to contrast that to address register indirect with pre-decrement, which may be the one you're thinking of, or with post-increment. Those pre-decrement and post-increment do change the content of the register. Okay? Thanks for the question. Okay, so that's one. That's very handy. However, there is yet one slightly more complicated indirect addressing mode, which is very useful. And its name is quite a mouthful. It's address register indirect, that's true, with, and we want to stick in here, index register, an extra register, and offset. Okay, so let's have a look at that. Let me write it down in our tariff here of costs, and then we'll talk about it. Address register indirect. So we have an address register being used as a pointer, that's for sure, with index register and offset. So this is the all singing, all dancing with the kitchen sink and everything else you can possibly think of addressing mode. And in spite of that, it's actually quite useful. Basically, if you think of it, you have there are two registers whose contents you can vary in the course of executing your program. There is the address register that's being used as a pointer, and there's also this other thing called an index register. Okay, and this is Motorola's own terminology for this. I'm not making this stuff up. Let's have a look at the format of it. Perhaps the format. Maybe we might even take an example. It might be just better to take an example. Suppose we, might even give you a use for this thing now, this stage. No, just keep it simple. Another use for this example later. Okay. Let's say we said I want to move a word, and I'm going to use the address register indirect with index register and offset now. So I'm going to say I want it to be 4 past. Well, let's say 8 past, and then I'm going to specify the address register that's in this addressing mode, say A3, okay? And now, rather than close the bracket, I'm going to put in an index register. Now, an index register in this situation is any register, be it a data register or an address register. Okay, so in Motorola talk about an index register. In this context, we're talking about any register at all, whether it's an address register or a data register. So let's say it might be D6. Okay, and the address that will be used to specify this operand or to find this operand is going to be the sum of the contents of the two registers, A3 and D6. I'm not finished, by the way. A3 and D6. And this fixed offset here, 8. So it's quite complicated. It takes the sum of the contents of A3 plus the contents of D6 plus this fixed value. This is fixed at assembly time. You write this in at assembly time. But at runtime, at execute time, you can vary obviously the these two indirect registers here. So typically, for example, you might use A3 here to point to the base of an array, and you don't know where that is until runtime. You make A3 point to it, and you might use D6 to index into the array. Okay, so you might use A3 here to point to the base of your array, and D6 to offset to index into it using a value you calculate or you get at runtime. So you'd use it like that. Now there's a further little variation here, so I just want to finish off here. You can specify the index register here to be used either as a word or as a long word. So .w or .l, not .b, unfortunately, either .w or .l. In other words, it'll take, as the effective address, it'll take the sum of the contents of A3 here, full 32-bit contents of A3, plus this index register as specified. If you specify a long word, it just takes it completely. If you specify a word, its sign extends its word contents when it's adding it to A3. So you'd have the address would be the contents of A3 plus the contents of, say, D6, sign extended if necessary, plus the offset, the fixed offset, which in this case is 8 bits, also sign extended. Okay, so the effective address then is like that, okay? And as Greg here was just pointing up, the contents of the address register and the contents of the index register are not changed by the use of this addressing mode. Okay? The overall address is calculated by, again, in sort of a hidden register. We can imagine a hidden address register. It's calculated to be the sum of the address register you specify, the index register you specify, possibly sign extended, plus this fixed offset, which would be sign extended. Yes, sir?
Is it a mode like that we could use for the lab tomorrow?
You could use it, yeah. You could use it with profit. Yeah, yeah, you could. The thing about it is, when you go back to the idea of the difference between a RISC and a complex instruction set computer, you can use addressing modes to imitate or emulate the effectiveness of that addressing mode. It'll just possibly take a couple more instructions. So if you can reduce the number of instructions by using this mode, fine. Okay. Now, here's there's a slight paradoxical thing working here. You have come across absolute memory locations, direct modes, a while back. Okay, and you're sort of fairly comfortable with them now, I suppose. And you'll also be fairly comfortable with address register indirect, perhaps a bit less comfortable. And this one here is a bit of a monster. There's a lot going on here. It turns out, when we go through the timings, that this addressing mode, complicated and all as it is to understand, is actually quite fast. Right? In fact, it's faster than absolute memory long. So there'll be many situations where you'll be saying to yourself, I'm not going to use that address register indirect with index register and 8-bit offset because it's too complicated. It might be complicated for you to figure out, but it's going to be faster by and large than using absolute memory long. So you find some speed freaks when they're really interested in getting the last ounce of speed out of a program. They will put some kind of a base address in an address register so that in lots of places they can make use of this address register index with, address register indirect with index register and offset because it's faster than using absolute memory long. Okay, so you have some funny situations like that. So there's two new addressing modes: address register indirect with offset and address register indirect with index register and offset. And real soon now we'll start looking at those seriously, but you can certainly use them for the practical if you want. Okay, let's take a few examples. Right? So what we have to do now, we know how extension words are accounted for. We now have to sort of just work through what actually goes on when an instruction is fetched and executed. We'll take a couple of simple examples first, and then we'll take a couple of fairly complicated ones. Okay, so simple example. We had a couple yesterday, so here's another one. Move a word from, say, D4 to A0. Looking at this very quickly, you can probably, by inspection, and I hope by inspection pretty soon, you could say, oh, look, these operands are both in the processor. They're both in registers. So the source operand and the destination, I should say, are both in the chip, in the processor. So we really just have to fetch the instruction, and there's going to be no more traffic on the bus apart from fetching the instruction. The instruction is going to look like this. The operation word will contain the move, the .w, the fact that the first operand is being referenced using data register direct, and that the register in question is D4. and the fact that the second operand is being referenced using address register direct, and that the address register in question is A0. So we don't need any extension words. There's no immediate operands, there's no memory direct operands, there's no indirect offsets required, so we're home and dry. We're in business here. Okay? So that means that it's going to require just to fetch the operation word. Everything else costs nothing. Okay? There's no put away, there's no operand fetch. Everything is on chip once the instruction has been fetched. Okay? So that's fast. That's one word fetch. Turns out, as we'll see in a while, that the 68000 hardware classifies bus transactions according to whether whether information is coming to the processor, that's called a read cycle, or going away from the processor, that's called a write cycle. Now, all processors do that. The 68000 also classifies bus transactions as to whether they're instruction fetching, like fetching this instruction here, or whether they're data fetching or putting away. Okay, so it distinguishes between data and instruction bus transactions. But that's very useful for security. Okay, so let's take another one. Let's take this one that looks perhaps a little bit like that one. Move a word from D0 to where A0 is pointing. Okay, now we'll have a look. So again, let's think intuitively here for a moment. A0 is being used as a pointer here, so it's pointing to memory. And what's going to happen with this instruction is the contents of D0, which is the contents are in the processor, are going to have to be sent out across the bus. They have to be written across the bus, away from the processor, out to somewhere in memory that's pointed to by A0. That's what's going to have to happen. Okay, but let's go through it. Okay, the operation word is going to have in it that it's a move, that it's a word size move, that the first operand is to be referenced using data register direct, and that the register in question is D0. That the second operand is to be referenced using address register indirect, okay, and that the register in question here is A0. Okay, so the full instruction, the complete instruction, is contained within the operation word. So it doesn't require any extra extension words. Okay, so there's going to be one word for the instruction fetch. Okay, but now we have to think about what happens when the instruction actually gets executed. Because what will happen, A0 will be pointing to some memory location. The instruction will cause the contents of D0, which is in the processor, to be written out across the bus out to wherever A0 is pointing. That's going to take, because it's a word size operation here, it's going to take one bus transaction. So we'll have one word data put away, or writing of the result, so to speak, of this transaction out into memory. Okay? Let's take another example. Oh, sorry, I should have left that. One word of instruction fetch and one word of data put away. Now let's take another example. Let's take the example of, say, move a word from location 1300 to D4. Okay, another simple example. Okay, again, just thinking of it intuitively, the big picture. What we know is going to happen is that in response to this instruction, the contents of the word that starts at location 1300 in memory, that word is going to be fetched across the bus and it's going to be placed in D4. That's what the instruction is going to get us to do, right? Or get the processor. Okay, so let's have a look at what happens. First of all, the instruction fetching. Okay, we'll have that the instruction is move that the size is a word, that the first operand is being specified using what? Using what? So here's our first choice. If we were the assembler, we'd have to look at this operand here. We say this is a memory direct operand, and are we going to access it, are we going to reference it using absolute memory short or long? And that's one of the gentlemen behind at the back there, at the foot of the stairs. AF92, your time is up. Or is it 82? Yeah. What do you think should happen? So I'll just re-ask the question. What I'm saying here is that we're trying to work out for the first operand what addressing mode we should use to specify it. Okay, it's obviously a memory location, so it'll be absolute memory. The question is, could it be short or long? Okay, and I don't mean to put you on the spot, so I'm sorry about that, but I do mean to get your attention. You can use absolute memory long, and you know that it's definitely going to work, but it's going to require 2 extension words, okay, for a full 32-bit address. If the address is between 0 and 7FFF, or if it's between FFFF 8000 and FFFF, the highest 32K, you can use absolute memory short. So here's an example of an address that lies in that lower range, from 0 to 7FFF, okay? Was that the answer you were reaching for? Yeah, thanks very much. Okay, so absolute memory short. Okay, so the fact that the first operand is going to be referenced using absolute memory short, that will be in the operation word, but not the address itself, because there just isn't room for it. The fact that the second operand will be referenced using data register direct, DN, and that the data register in question is data register 4. Okay, so if you like, that's a picture of what will be in the operation word for that particular instruction. So we need one extension word to store this absolute memory short address. And that's going to take up one extension word, which will contain 1300. So the instruction is going to be 4 bytes long, 2 words long, not just 1 word long. Okay, so it's going to take 2 fetches, 2 bus transactions, 2 word fetches to get the instruction. Okay, then the instruction has to be given effect to. And so the word that's at location 1300, that word has to be brought in from memory across the bus into the processor. So we'll have 1 word data fetch. So we know, and that's it, right? Because it's landing in a data register, and that's the end of the instruction. We know, therefore, that this instruction is going to take 3 bus transactions to execute. So the very first instruction we had is just 1 bus transaction, half a microsecond. This one is 2 bus transactions, a microsecond. This one is 3 bus transactions, a microsecond and a half. And so on. Okay, you can work it out. Let's take the most expensive move instruction that I think there could be. Oh, well, let's take 1 more first. Here's another one. And I'm deliberately trying to keep these looking somewhat similar because I don't want the extraneous details to confuse you too much. So here we have 1300 to D4. Okay, so we're saying I want to move a word whose immediate value is hex 1300 into D4. Previous example, I want to move a word that's at location 1300 into D4. Okay, this is different. So again, intuitively what's going to happen is when this instruction is over, the value 1300 will be in D4. So the instruction is going to have to be fetched first. Let's have a look at that. Okay, so what's going to be in the operation word is the fact that it's moved, the fact that it's a word, the fact that the first operand is immediate. Let me just put that down here as using the hash sign, that it's immediate, and that it's a word that has to be fetched. Now, that's an immediate operand. It's going to be part of the instruction. It's going to take up 1 extension word. Okay? And so the fact that the second operand is data register direct and that the data register in question is D4. So that's what's going to be in the operation word. The move W immediate D4, but not the value of the immediate operand. Okay, so that's the operation word. And then the extension word will have 1300 in it. Okay, so the instruction then is 2 words long, in 2 fetches. For the instruction. Okay, now you have to be very careful. What happens next? Okay, we can imagine that the instruction the entire instruction has been fetched at the cost of 2 cycles and is now in the processor. Okay, the operation word and the immediate operand. So what has to happen next? Yeah, the value gets moved. It's in the processor. The value 1300 is in the processor because we fetched the whole instruction. And that just gets transferred to the register. The register is in the processor as well, so there's no extra cost. Okay? So no data transactions. Okay? So that instruction then is going to be 2 bus transactions. This one here is 3, this one here is 2, and this one here is 1. Okay, so you can begin to see how you can actually work out how long an instruction is going to take, both in terms of the actual length of the instructions encoding and how long it's going to take to execute. Okay, so you just go on like that. Now, let me take for a finish today, I'll just take the worst, the most expensive move instruction that you could imagine. It could be something like this: move a long word from location, say F0, 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 F0 to location FA, 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 FA. Okay, so that's a move instruction, and this would be legal. This would be a legal instruction in the 68000. Okay, again, you need to bear in mind what actually is going to happen. It's not the case that information will go directly from this location to that location. It has to come down through the processor. And because the bus is only 16 bits wide, it's going to have to come down word by word. So one word will come down from this location to a hidden register in the processor, and that will be written up to this location here. And then the second word will be read from this location and written up there. I don't know what the exact physical ordering on that is, whether it's read, write, or read, write. I don't know. And I imagine it varies from implementation to implementation. But very quickly, let's just look at the encoding of this. The encoding, okay, move a word and it'll be absolute memory long. Will be the way the first operand has to be specified. Okay, absolute memory long, because you can see it's well outside the ranges for absolute memory short. First 32K or the last 32K. And likewise, the second one, absolute memory long. I'm sorry, I've made a mistake here. What we're talking about is move.l, move.l. Okay, move.l. So the fact that it's a move, the fact that it's a long word, the fact that both operands are referenced using absolute memory long, that will be in the operation word. And then we need, we need extension words. We need to specify an absolute memory long address. That's a 32-bit quantity, so it's going to take 2 extension words. So that'll be the first address, and the same then for the destination address. So that will be specified here. So that means the instruction is 5 words long, so it's going to take 2.5 microseconds to fetch the instruction. Okay? So now, what about actually executing the instruction? As I indicated there just a moment ago, you're going to have, once you have the full instruction in memory, you then have to go and get the long word operand that's at location FO, 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 FO. And that's going to take 2 word reads. And you're going to have to then move it out to this location, FA, 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 FA. You're going to have to take 2 words in and push 2 words back out into memory. So that means that there's going to be 5 words for the instruction, fetch, 2 words for the instruction for data, read or fetch, and 2 words of data write or put away. So that means that this instruction here takes 5 and 4 is 9 bus transactions. 9. So it's almost an order of magnitude, almost 10 times slower than the fastest move instruction. Okay? So that just gives you an idea of the span of these things. Okay, we'll talk a little bit more about this on Thursday. Thanks for your attention.